Instrumentation of mass spectrometry, components, working and mass analysis of ions. Hello everyone, welcome back to Chempoetry. In today's video, we will learn about the instrumentation of mass spectrometry, one of the most powerful analytical techniques used to determine molecular mass and identify unknown compounds. We will understand each component, its function, and how ions are separated according to their mass to charge ratio, commonly written as M/Z ratio. So let's begin. Instrumentation of mass spectrometry. First we discussed. A mass spectrometer consists of several important components. These are Sample Inlet System, Ionization Chamber, Acceleration Chamber, slits, Mass Analyzer, Detector, Amplifier and Recorder. Each component performs a specific function and together they produce the mass spectrum of a compound. Then the first component is Sample Inlet System. The first component, Sample Inlet System, its main function is to introduce the sample into the instrument. The sample may be solid, liquid or gas. Before ionization, the sample is converted into vapor form and introduced under reduced pressure. So one question is there, why is it important? Because it provides a continuous sample supply, prevents contamination and ensures efficient ionization. In simple words, the sample inlet system acts like the entrance gate of the mass spectrometer. After entering the instrument, the sample reaches the ionization chamber. The function of this chamber is to convert neutral molecules into positive charged ion. Its construction includes a heated tungsten filament, electron source, high vacuum chamber. Its working is the heated filament emits high energy electrons. These electrons strikes the sample molecule and remove an electron from them. The reaction can be represented as M plus E negative gives rise to M positive radical plus 2 electron, where M is the sample molecule and M plus radical is the molecular ion. The ionization step is essential because only charged particles can be manipulated by electric and magnetic fields. Once ions are formed, they enter the acceleration chamber. Here a high voltage is applied, causing all ions to gain kinetic energy. The kinetic energy acquired by an ion is half mv square equal to EV, where m equal to mass of ion, v equal to velocity, small e equal to charge, v equal to accelerating voltage. This chamber ensures that ions move at high speed towards the mass analyzer. An important point is that all ions receive nearly the same kinetic energy before separation. Then, now let us derive the fundamental equation used in mass spectrometry. From the acceleration chamber, half mv square equal to EV. In the magnetic field, the magnetic force provides the centripetal force. Therefore, HEV equal to mv square by R. Simplifying the equation, HE equal to mv by R. Squaring both sides and we get h square e square by h square e square equal to m square v square by r square. Substituting m square v square equal to 2 EVM. Then we obtain m by e equal to h square r square by 2v. This equation shows that the mass to charge ratio depends on the magnetic field strength, radius of ion path and accelerating voltage. The mass to charge ratio or M by E ratio is the basis of ion separation in mass spectrometry. Large M by E ion show less deflection and small M by E ions show greater reflection. Heavy ions follow larger circular path, while lighter ions follow smaller path. Thus, ions with different m by e values can be separated and identified. After that, we discuss about the types of mass analyzers. There are different instrument uses different mass analyzers. The major types are magnetic sector analyzer, double focusing analyzer, quadrupole analyzer, time of flight or TOF analyzer, FT-ICR Analyzer. A quick mnemonic to remember them is MDQTF. Magnetic sector, double focusing, quadrupole, time of flight and FT-ICR. This analyzer uses a magnetic field to separate ions according to their m by z values. Heavier ions are deflected less, while lighter ions are deflected more. This double focusing analyzer combines electric and magnetic fields. It provides very high resolution and improves mass accuracy. So, second is the quadrupole analyzer, which consists of 4 parallel rods. By applying radio frequency and direct current voltage, only ions with specific m by z values passes through. It is fast, compact and widely used. Then TOF analyzer. In this analyzer, ions are accelerated to the same energy, and lighter ions travel faster and reach the detector fast. Heavier ions arrive later. The flight time is used to determine m by z values. Then last is FT-ICR. FT-ICR stands for Fourier transform ion cyclotron resonance. It uses strong magnetic field and provide extremely high resolution and accuracy. It is mainly used for advanced research application. After separation, ion reaches the detector. The detector converts ion impacts into electrical signals. Common detectors include Faraday cup electron multiplier. A signal produced is usually very weak. Therefore, it is sent to the amplifier, which increases the signal strength. Finally, the recorder records signal intensity against m by z value and produces the mass spectrum. Let us quickly revise the sample and toss through the sample inlet system. The neutral molecules are converted into ions in the ionization chamber. The ions are accelerated in the acceleration chamber. The mass analyzer separates ion according to their m by z value. The detector detects ion. The amplifier transcends the signal, and the recorder produces the mass spectrum. This is the complete working of a mass spectrometer. If you found this video helpful, please like, share and subscribe to Chempoetry. Don't forget to press the bell icon for more chemistry lectures, spectroscopy concepts and exam-oriented content. Thank you for watching and keep exploring the beauty of chemistry. Jai Jagannath.